Okay, so today I will talk about this recent work on a semigroup method for high-dimensional committor functions based on neural network. Okay, so first, let's review some background. Real events includes many phenomena in nature, such as chemical reactions and conformational change of biomolecules. So it is called rare because the vibration of chemical bonds typically occurs on a timescale of picoseconds to femtoseconds. But reaction typically takes seconds or longer to occur, so it is very rare in this sense. So before going to the model, let's look at some intuitions of the system dynamics. This part is adapted from a review paper by Eric and Weinan. So we assume that a potential function is defined on the phase space of the system, and there are two metastable states called the reaction state A and the product state B. There are two local minima of the potential function, and there is some barrier between A and B, and the system is subject to some noise, which leads to transitions from one state to another. But the noise is relatively small compared to the barrier, so the transition is very rare. So we want to model the dynamics between A and B, and we want to know that the transition mechanism and reaction rate and so on. So one typical theory is the transition state theory, which states that in order to go from A to B, the system has to go to a settle point first on the potential energy landscape. Another example is the large deviation theory, with which you can calculate the most probable transition path. But there are some limitations of these two examples. So for example, in TST, it is assumed that every crossing of the transition state leads to a transition, which may overestimate the reaction rate. And the barriers may be entropic, so the settle point on the energy landscape may not play the role of a transition state. And there can be an ensemble of paths contributing to the transition instead of just the most probable path itself. Okay, so in order to address these limitations, the transition path theory was invented. So the system dynamics is modeled by the Landry equation. Here we only consider the overdamped case. For this overdamped Landry dynamics, we can define the corresponding backward operator and forward operator L and L star, and also the equilibrium distribution rho, which satisfies L star rho equals to 0. The central object in TPT is the committor function, which is defined by the probability of hitting region B before region A. And by the definition, we can show that the committor function satisfies a Fokker-Planck equation like this. And the committor function is important because by the committor function, we can calculate the transition rate, the probability density of reactive trajectories, and the reactive current, and so on. So there are some difficulties in calculating the committor function. For example, the phase space can have very high dimensionality, and the committor function has singularities. For example, in the high temperature regime, the committor function can be steep near A and B, because in that case, the Fokker-Planck equation converges heuristically to a Laplace equation. And in the low temperature regime, there's typically a sharp interface around the transition area between A and B. And we need to enforce a boundary condition, and large penalty terms may lead to a yield condition problem. Okay. So in the previous work, high dimensionality of the phase space is addressed by parameterizing the committor function with the neural network. And then we can derive a variational form of the original problem and solve corresponding optimization problem with respect to the parameters. And the singularity of the committor function is handled by using explicit singularity terms and 10H activation for the last layer. In this figure, n theta 0 uses 10H activation and the last layer, which fits the sharp interface around the transition area. And SA and SB are two singularity terms which has the form of fundamental solutions to Laplace equations. But the enforcement of the boundary conditions is still done by penalty functions. So more specifically, instead of the original strong form, we consider this corresponding variational form, and these two boundary conditions are enforced through penalty functions. So clearly, there are still two problems in this method. First is that there is an explicit differentiation in the objective function, which is here. So when using gradient descent method to solve the optimization problem with respect to theta, you need to calculate mixed second order derivatives with respect to theta and the original variable. So that's the first problem. And the second problem is we need to carefully tune the penalty coefficient because the boundary conditions are solely enforced through the penalty terms. So intuitively, we can consider I minus e to the delta LQ equals to 0. Instead of LQ equals to 0. In that way, the explicit differentiation is removed, and we can use Monte Carlo methods to simulate this operator. We'll see later that the boundary conditions can be integrated into the semigroup operators as well. So rigorously, we can prove that under some conditions, the committor function satisfies this formulation, where the semigroup operator P is defined as this expectation taken with respect to the law of the Landry process at tau wedge delta, where tau is the smaller one of tau A and tau B, and tau A and tau B are the heading times of region A and B. So we can use Dinkins formula to prove this proposition. And then we observe that this operator can be split into two parts. So when delta is larger than tau, x tau wedge delta belongs to the boundary A or B. So we can replace the committor function by the boundary conditions. Here R is the boundary function, which is equal to 0 at the boundary of A and 1 at the boundary of B. So in this way, we can express the original equation in this way, and the boundary conditions are naturally integrated into the function itself. So we also want to work on the variational formulation. So we need to prove positive definiteness of PI. And we can show that PI is symmetric on this L2 space weighted by the equilibrium distribution. So we can derive this variational formulation using the semigroup operators. And then we parameterize the committor function by a new network. And in order to achieve a better performance, we also add the penalty terms here. But the important difference between this formulation and the formulation in the previous work is that here we don't need to tune this penalty coefficient. We will show that in numerical parts. Okay. And in order to implement S3D type methods, we need to calculate derivatives. So luckily, these derivatives can be expressed by an expectation taken with respect to x and x delta. So in order to give an unbiased estimator, we only need to give samples of x and x delta. So basically, we solve the Landry dynamics by Euler-Maruyama scheme. And we also approximate the corresponding indicators with using discretizations. And we also use multi-step Euler-Maruyama scheme to improve accuracy. Okay, so let's look at some numerical examples. The first one is on the double well potential defined on the first dimension. So in this case, the total dimension is 10. And we can see that with hundreds of thousands of training samples, we can achieve a final precision of 0.01. So here, this error is defined by the relative error between the committor, approximated committor function, and the ground truth. So in this figure, we compare the neural network committor function and the ground truth along the first dimension for an arbitrarily chosen x2 to xd. You can see that the approximate solution is very close to the ground truth. And we can also show that the final error is not sensitive to the parameter delta. If we use different deltas, we obtain basically same final errors. Okay. And more importantly, we don't need to tune the penalty coefficient. So in this figure, we show that using the current method, the training behavior and the final precision are about the same with different penalty coefficients. But in the previous method, when you use different penalty coefficients, you obtain very different final errors and very different training process. So in that sense, the previous solution, the previous method is much more sensitive to the penalty coefficient. Okay, and we also tested on the rugged motor potential, which has a rugged landscape on the first two dimensions. So in this figure, we show the equilibrium distribution on the first two dimensions. Here, region A and B are cylinders, and these two figures are drawn on the temperature 22 and 40. And we also obtain very good final precision with several 100,000 training samples. And the last numerical example is the Ginsburg-Landau potential. So it is obtained by uniformly discretizing this Ginsburg-Landau energy in one dimension. Okay. So the region, the potential has two local minima as shown here. And the regions A and B are taken as the both Euclidean balls around these two local minima. And in order to verify the result, we first identify M states on an approximate 1/2 isosurface. And then for each state, we generate N trajectories according to the non-trivial dynamics, and we calculate the number of trajectories that reach B before A. And we compare this distribution to the ground truth distribution, which should be approximately a normal distribution. So we can see that the empirical distribution is very close to the ground truth from this empirical PDF and the quantile plot. Okay, so in conclusion, we show that the committor function satisfies an integral equation based on the semigroup of the differential operator. And we remove the explicit gradient and handle the boundary conditions naturally. And we also show the convergence of the training process in the lazy regime. And the resulting algorithm is shown to be faster and less sensitive to the penalty parameter than the previous method. So for future work, we can integrate important sampling techniques in the sampling process or adopt higher order integration schemes instead of Euler-Maruyama. And we can also apply this method to other high-dimensional PDEs and eigenvalue problems, which is already done in another recent work. And thanks for your attention.